Hi everyone, in this lesson we will solve an example question about Brighton cycle with ideal regenerator. Let's look at our question and given values. In a gas turbine power plant operating on the Brighton cycle with regenerator, the fluid circulating in the cycle is air, regenerator efficiency is 100%. The air enters the compressor at a pressure of 100 kPa and a temperature of 25 degrees Celsius, and enters the turbine at a pressure of 800 kPa and a temperature of 900 degrees Celsius. There is a heat transfer Qn, which means of 65,000 kilojoule per second to the air in the combustion chamber. The net power of this power plant, assuming constant specific heats at room temperature, calculate the variation of specific heats with temperature, and calculate the annual savings by using the regenerator in this turbine that uses natural gas as fuel. Find the depreciation period of the regenerator system installed 20 million Turkish liras. For natural gas combustion efficiency, the ITA 0.9. The units per meter cube price is 24.38 Turkish liras. That's taken from the İzgaz September 2022 tariff table for electricity producers. İzgaz is a company which provides a natural gas to nations, to Turkish nation. Lower heating value for natural gas is HU and 35,500 kilojoule per meter cube. So let's look at or solve, but before the look at our solution, we need to remember our TS diagram again. So don't forget about our TS diagram like this. Our TS diagram will be like this. Or air enters the compressor at a pressure of 100 kPa, which means the P1 at there is the compressor and there is the turbine. The P is constant between 2 and 3 and between 1 and 4. So the temperature of 25 degrees Celsius, it's 298 Kelvin for T1, and enters the turbine at a pressure of 800 kPa for P3, and temperature of 900 degrees Celsius. It's T3 900 degrees Celsius, which equals to 1173 Kelvin. There is a Q in 65,000 kilojoule per second. So let's look at our solution, detailed solution. Here is our TS diagram for Brighton cycle with regeneration, as you see, and we can determine the RP number from that given values. We can divide the P2 to P1. P2 equals P3 because the P is constant between 2 and 3 and between 4 and 1. So our RP number is 8. So we can easily determine the T2 value according to our RP number, the power of chi minus 1 divided k cross T1, and it will be equal to 539.811 Kelvin, and it will be equal to our T6. They will be equal at the diagram. They look like different, but they are the same value. It can be a little mistake at diagram. Then we can easily determine our T4 value, but we need to divide this time to our equation. So our T4 will be equal to T5 for a theory, and it's 647.55 Kelvin. Then we can easily determine the Q in according to equation with M cross Cp cross T3 minus T5. So the Q in has already given in that question. It's 65,000 kilojoule per second. So it's equal to that equation. We can easily take the mass flow rates from there, and we can easily determine it. it will be the 123.09 kilogram per second. Then we can easily determine the Q out according to our M value, and we can wrote it at there, and our Q0 Q out value is 29,913.21 kilojoule per second. Then we can easily determine our net and net. It's equal to differences between Q in and Q out, and it's equal to 35,086 kilowatts. And if we look at the second part of our question, the T1 is equal to 298 Kelvin. We can easily determine the H1 and PR1 value from the table A17. It's 298.18 kilojoule per kilogram and 1.3543 kilopascal. So here you see, and our P2 divide P1, it's equal to RP, and it's equal to P3 divide P1, and it has to be equal to PR2 divide PR1. We already know PR1 from that table, so, and we know the RP value, it's equal to 8. Then if we cross that two values, we're gonna gain that PR value, it's 10.8344. Then if we look at the thermodynamic table A17, 10.8344 is between that two values, 530 Kelvin and 540 Kelvin. We're gonna make a linear interpolation for this question to determine the better result. So we're gonna wrote the first value and the second value at there. Then our value is 10.8344. And its our temperature is 536.3614. Here you see, we can do the same thing to our enthalpy value, and we're gonna gain that value 536.36 kilojoule per kilogram, and they are equal to H6 and T6 according to our TS diagram for regenerative Brayton cycle. Then we can determine the T3 from the A17 at same way, and it will be equal to its enthalpy and PR value are equal to these numbers. Then we can determine the PR4 according to our RP value we already have now. And if we can look at that RP force value at A17, or H4 and H5 is 701.26 kilojoule per kilogram, and or T4 is equal to T5, and it's equal to 689 Kelvin. So our Q in value is M mass flow rate cross the differences between H3 and H5 enthalpy values. So we already know it's 65,000, and 65,000 is equal to M cross H2 minus H5. So M is 119.29 kilogram per second. So our Q out value is M cross H6 minus H1. It's equal to 28,915.90 kilojoule per second. So our net work and net is equal to Q in minus Q0, and it's equal to 36,084.10 kilowatts. So let's calculate the Q regenerative and Q earning money saving. The saving energy. Then we're gonna calculate the saving money. Q regeneration is equal to M cross H5 minus H2. We all know that values minus Q regeneration. It's equal to 19,167.51 kilojoule per second. Then let's calculate our money. Our Q regeneration is will be the 0.60 meter cube per second saving. 0.60 meter cube per saving is if we can cross it to 60 for minutes and cross 60 for hour, then cross 24 for day, then cross 365 for year. It will be the 18,921,600 meter cube per year saving, and our annual earnings will be the in Turkish liras. If we can cross that value to 2438, it will be the 461,388,608 Turkish liras per year. So it's depreciate, it pays for itself in only 16 days. It's a very good system, very budget system for us. So that was our solution. See you in the next lesson.